Well, then we are going to talk about a new topic. So that's called the force. Or we call it dynamics. Okay, that is the study of force. Actually, a long time ago, there's a lot of scientists, but this is not a scientist that study the force. So Aristotle, and then the next one, Galileo. The next one is Newton. 不頂，有寫錄低咗添。好，now then we will just ignore these two guys, okay? So we just talk about the Newton's law of motion first. I think all of you have some idea of about force. So let's talk about the Newton's law of motion. In your IGCSE, I think you have learned about the Newton's second law only. We don't emphasize the first law and the third law, although it's in your textbook. So let's take a look at the Newton's first law, and then go to the second law, and then the next one is the third law. Just lazy typing, okay? Or smart, okay? Smart guy will do it like this. Let's talk about the Newton first law. The statement is like this. So the statement is say that if there's no net force acting on an object, then the object will remain its inertia. Or just say remain its motion. So what does mean by remain its motion? That means if the object is initial at rest, then it will remain at rest. If the object is moving is initial moving, right, then it will continue its okay. If the object is initially moving, then it will remain moving at the same velocity. Now I think I've talked about this already. If object is moving at same velocity, that means the motion is a constant velocity motion. If the object is moving at constant velocity, that means the object is moving along a straight line. Because when we say about the constant velocity, so that means the direction of motion does not change. So therefore, it should be a straight line. So this is about the Newton's first law. But indeed, we don't use the first law for any calculation. So we mainly use the second law, or sometimes the third law. So let's take a look at the second law. I think you have learned about this already. So net force your MA. But I want to emphasize something about the Newton's first law. So if the object is moving, does it mean that there should be a force acting on the object? Kenji, what do you think? Well, Kenji, 叫你名都唔知。Kenji， 你啱啱瞓醒啦。So if the object is moving, does it mean that there should be a force acting on the object?
No.
Yeah, when we say the object is moving, it can be no force acting on the object. You think about the case, there may be if the object is moving, it doesn't mean that there is a force acting on the object. So you just think about a case, it's just a spaceship. Because we cannot find an example on Earth. All the objects on Earth that the Earth is attracting it, or the force, you call the force gravity or the weight. So let's think about the case of spaceship in a deep space. Okay, deep space, it means that okay, this is a region there's no any planets, no any stars, or any objects, any masses nearby. So in that case, okay, the spaceship can still move with constant velocity, without any force, without turning on the engine. So that is, I think this is the only example I can think of. So, but if you're talking about the examples on Earth, so let's say there's ice skiing. 點算？錯。好，嗱，why I use this as an example because we say that the friction on ice is pretty small. You can ignore that friction. And if you push some guy standing still on this ice, okay, then this guy it can move along a straight line forever until it drops into the sea. So this is another example. 得食個水果先。And let's take a look at the Newton's second law. So I think all of you have learned about this one already. But I want to emphasize that this formula is actually a vector. So that is a net force equal to ma. And first of all, I also want to emphasize what net force means. So net force is the sum of the vector sum. If you still remember, we have learned about how to the vector addition. So you need to make use of that skills to add all the vectors together. This is a vector sum of all forces, okay, all forces are acting on that object. That is a force acting on that object. You don't count the force acting on another object. Okay, you will know that why I need to emphasize this one later on. So and then what this formula applies is there is a net force is actually, net force is a vector, and acceleration is also a vector. So net force is parallel to the direction of is parallel to acceleration and in the direction of acceleration. So that means if the acceleration is pointing to the left, then the net force is also to the left. Okay, simple. Let's go to the Newton's third law. So the Newton's third law is a bit more complicated, I think. You don't know when you need to apply it, but I'll tell you later on. So it states that if object A has a force on B, then B will add a force on A. And this pair of force is called action and motion pair. First of all, I want to emphasize, in English, if you say something, if something, then something, you will say that this is a cause. You may consider that this is a cause, and then this is an effect. Is it? Now, indeed, this pair of force is not a cause and effect. What do I mean? Now, if you say something cause and then something effect, you will say, okay, the cause happened first, is it? Then the effect will just happen later. But indeed, for these two things, they happens at the same time. Okay, do you understand what I mean? They happen at the same time. So we can't call it the cause and effect. So in physics, we call it the action and reaction. I think this term is quite confusing also, because you say action, reaction is something like cause and effect, but it isn't. Okay, Then let's take a look at the properties of the action and reaction pair. This means all the forces have its partner. There's no force that is alone in this universe. Unlike Kenji, okay? The property of action and reaction pair, there's a few properties. Let's take a look at the first one. So they have equal magnitude. But they are opposite in direction. They add on the same line of action. I'll talk about this later on. And then they will appear and disappear at the same time. So that means they are not cause and effect. Maybe I can think of one examples. In reality, let me think. Oh, no, I can't think of one example. Okay, so there are four properties. So sometimes in the textbook, I will say about the fifth one. The fifth one is like, okay, they're acting on different objects. They are acting on two mutual objects. Sorry. The forces are acting on the two objects mutually. But actually, it's just repeating what is stated here. Okay. So let's take a look what is line of action. Line of action. Good. So there's an object A. So there's an object B. So if A has a force on object B, sorry. So when I draw an arrow here, it means that this is a force acting on the object A. So this is a force on, we say on A by B. And so the force acting on B by A. So these two forces have equal magnitude. So they should have the equal length. And what does it mean by the line of action? So this force must act on some point on object A. So this is a point where the force acts on. This point we call the point of application. So this is the point where the force acts on. Okay. So when you extend, you consider there's an imaginary line passing through the point of action and also parallel to the force. So these two forces will be on the same line of action. Okay. Although I don't think it's quite important for this commission, but it's still a property. It's one of the properties of the action reaction pair. Is it clear? Now let me think. Let's talk about another example. So let's say, for example, there's a sun. Good. So there is an Earth. So you know the Earth is attracted by the sun. But you need to know that at the same time, the sun is also attracted by the Earth with same magnitude, opposite direction, act on the same line of action, appear and disappear at the same time, and also acting on the Earth and acting on the sun mutually. Okay, so this is a line of action. Okay. So these two forces have the same magnitude. Okay? Although you may think that okay, there's no force acting on something because it's so massive, but no, these two forces are equal in magnitude. Just another example is so do you know what I'm drawing? Do you know what I'm drawing? Do you know what I'm drawing? Oh, RPG, do you know what I'm drawing? Yeah, that's an airplane, okay? Wow, you know me you know me so well, okay? Oh. So do you know for an airplane? So what does ah oh so do you know what is the pilot afraid of? So the pilot afraid of the bird. Do you know why? Like, this is not the bird. This is the bird. Okay. Now you think that okay? I think obviously, if the airplane is traveling in the air, you think that okay, it's traveling at high speed, and if another bird is moving towards the airplane and hitting the grass, I think you think that okay, the bird will experience a large force by the airplane, and then most likely it will die. But you need to think about but considering the Newton's third law, you know that it also exerts the same amount of, so the same magnitude of force on an airplane. So most likely the glass on the airplane will also break. There's some cases, alright, yeah. You can search that online. You can Google it, and then the window break, and then the aircraft may crash, just may, okay, but in reality, nowadays it won't, and that's why the airplane will almost fly a very high altitude. Is it? Very high height, and then at that height, there's no bird flying there, so no worry about that. We have already finished talking about the Newton first law, second law, and third law. And then we are going on to talk about different types of forces, one by one, okay? So the first one, the most easiest one, is the weight of the object. Now the weight is actually the gravitational force on the object by the Earth. Now I don't want to hear something like that, okay? Sorry. I think there's many misconceptions about this one. So many people may think that, okay, let's say the object is resting on the ground. Hold on. So there's a guy resting on the ground. Now many people may think that so the weight is the force acting on the ground by K. Is it? Do you have this concept? So some people may think that the weight is the force acting on the ground by K. So that's wrong. Why? Do you know why? Actually, if you're talking about the force acting on the ground by K, that's another force. It's not the gravity by the Earth. And also, you know that if the K jumps, then he is not touching the ground. This force does not exist at the time. But you know the weight always exists. So the weight is not the force acting on the ground by K. So and then let's take a look at how can we find its magnitude. You know for a vector there's a magnitude and also a direction, and also we need to emphasize on the points of application, the points where the force acting on. 好 I need to copy it down first because I just want to be lazy. 好，噔噔噔。好 let's take a look about the magnitude. I think all of you know about the formula, that's WMG. Do you? Do you still remember how do we prove this formula? Anyone? Anyone? No? Now you just consider there's a region there's no force, no air resistance. And if you drop an object, so the weight is the only force acting on this object, is it? Then the net force by applying the Newton's second law, then the net force will be the weight acting on the object by the Earth. And M is the mass of that object. And A will be the acceleration due to gravity. That's G. If on the Earth's surface, it should be 9.81. So that's how we derive this formula. Okay. So and then what is the direction of the force? So this the direction of the force is pointing. Now many people will say that pointing downwards. Yeah. To be more specific, I will say they're pointing towards the center of the Earth. Okay. 咦？點解彈咗過去？I'm center of the Earth. Okay. 好。Now let's move on. So and then where is the point of application? So this point we actually define as a center of gravity of the object. We will talk about this later on. But I think weight is pretty simple, is it? Any question on this force? So this force is pretty simple, is it? Any objection? No. Center of mass is not exactly the point. Center of mass and center of gravity, they have different definition. In most of the case, we'll just consider them at the same point. I'll talk about this later on. So let's take a look at the second force. So we call it the normal reaction. There's a different name for it, so you may call it the normal force. Okay, normal reaction or normal force. Or sometimes in the Chinese book they call it the supporting force, but you won't see this name in English textbook. So we just call it the normal reaction or normal force. So first of all, what does the normal mean? But the normal, it means in mathematics, it just means the perpendicular. So for its magnitude, actually we don't know about it. There's no formula like the weight. We cannot determine the magnitude directly from some formula. We need to apply the Newton's second law. Same as most of the forces. 好啦， then its direction is perpendicular to the surface. We're talking, so you need to take a look at some examples. But first of all, let me tell you what is normal reaction and why there's a force normal reaction. So when the two objects, okay, this force exists when two objects are in contact with each other. Contact. Let's take a look at one example. No need to take a look at one second. Just take a look at why these forces exist when the two objects are in contact. So there's an object resting on the ground. Again. So you know all the objects are made of atoms. So when the object is resting on the ground, the atoms are actually squeezing each other, or you just say that the atoms is actually they are put in when they're in contact. That means they are very close to each other, and you know the surface of the atom are electrons. So you can see, okay, in this region, the electrons are on these two surfaces are very close to each other. So you know same charge repel. So that's why these electrons are repelling each other. I do think you have this experience. So let's say if you are clapping your hands, the harder you clap, the larger the force you can experience. So that means if you push these two electrons closer to each other, then you will experience even a larger force. Yes. So that's why if this object is more massive, then this repelling force will be larger. So the origin of the non-variation is actually, sorry, let me save the file first. So the origin of the normal variation is actually the repelling, we call the electrostatic force. On two contacting surfaces. Now just keep it in mind, this is very important. Because later on you will just forget this statement. So the normal variation exists when two objects are in contact. Whenever you see that two objects are in contact, then that means there is normal variation. Okay. So let's take a look. And also that's why the force is perpendicular to the surface. You can see the repelling force on the electrons. 好啦，嗱 let's take a look at some of the examples here. So now if an object is putting on a wedge or on a slope, so the non-variation will be perpendicular to this surface. So it should be, it is not vertical anymore. So the non-variation will be perpendicular on this surface. And you know this is a repelling force. So this is the arrow, this is a normal variation. We use a symbol N or R. So this is a variation force acting on the object. Now by applying the Newton's third law, so the slope exerts a force on the object. So that means the object also exerts a force on the slope. So these two forces are action and reaction pair. So this is the normal action acting on the slope. Okay. So let's take a look at some other more complicated example. So let's say this is a bowl. How can I draw it better? No. So let's say if you put a chopstick on the bowl. Oh. Now this is a bit complicated. So because we are talking about a perpendicular to the surface. So let's say at this point. So at this point. So how about the surface? Does it mean this point, this surface, or this surface, or this surface? So we need to talk about the surface that is the tangent to this point. So that means we are talking about this surface. And then the normal action acting on the chopstick should be perpendicular to this surface. That means this tangent line. So the normal action will be pointing somewhere like this. and this ball is a semicircular ball, okay? I can't draw it. This is the best I can draw. Now, then this actually that actually points to the center of the semicircle. Can you see it? Can you imagine it? Most likely no, is it? No? Yes, no. Now this is one property about the circle. So let's say this is a circle. So this is a tangent line on the circle. Then its perpendicular direction should point towards the center of circle. It should pass through the center of circle. Okay. So therefore this non-version point towards the center of circle. I think it is somehow in one Olympic question. So I think I turned off the speaker. Can anyone speak?
Yeah.
Hello.
I can't hear. Sorry, can you speak again?
Hello.
Yeah, hello. So the non-version at another point should be tangent to the chopstick surface. So it should point something in this direction. Let me call it N1 and N2. Now because we don't have many symbols to represent the non-version, so you may just label it as N1, N2 if they add on the different points. Now how about the magnitude? We need to apply the Newton's third law. Now the points of application equals to the points of contact, or some points on the contacting surface. Now the points of application of the non-version can shift. Now just very simple example. So this is a guy wear a shoe. Now, okay, I think you can experience this. So if you move your body a bit forward, okay? Okay, if you move your body a bit forward, okay, without moving your feet, and then you can feel that the non-version acting on your feet by the ground will shift to forward also. So this is one example that you can experience. So the point of application is just on some point along the contacting surface on your shoe, but we cannot tell exactly which point is, unless we get the information of all other forces acting on you. We can find the point of application. In the next topic, it's called the moment. So that is the second force. Okay, so this is the normal version. Any question on this? Any questions? No,係咪? Then let's take a look. So let's go to the third force. Okay, the third one. So the third one is called the tension. Now we don't have a relation that larger the mass, the larger the non-version. No. We don't have this definite rule. So I don't consider there's a rule for the magnitude of non-version. But if you're talking about an object, maybe let's take a look at how we can apply the Newton's second law to deal with these kind of questions. So let's take a look at one example. So the first example is like this, okay? Let's say this is a ground. So this is an object with the mass 2 kg lambda. So the object is resting on the ground because it's contacting with the ground. So there must be a non-version acting on the object by the ground. So there is a non-version. So when we draw the non-version, the point of application is on the contacting surface. So you don't draw the arrow like this, okay? If you draw the arrow like this, that means the point of the application is at this point. So we draw the arrow from the contacting surface. So another force is the weight acting on the object by the earth, is it? Now you know if the object is at rest. At rest, that means by applying the Newton's second law, the acceleration should be 0. Then the net force will be 0. Then you know that these two forces should balance each other. So I will say that N equal to W. That's equal to mg. Okay. So let me apply another. Let's talk about so how about this example? So in this example, it's quite similar, but you exert another force on the object. Let's say if you push a 30 Newton force on the object. How about the normal motion? The normal motion will change. But in this case, yeah, the object is still at rest. And then you know that also, so there are two downward forces and one upward force. So in this case, the upward force N should be equal to the sum of all the downward forces, so that the object will be at rest, or so that the normal motion is 0. So if you compare the example 1 and 2, so of course the normal motion on example 2 will be larger. OK， 好啦，嗱 quiz time 啦嚇，好啦，嗱 let's take a look at one very simple example。好。So let's say there's 1 kg object, there's a 2 kg object. So 1 kg object is put on top of the 2 kg object, and both objects are at rest on the ground. Let me draw it better 啦，好唔好？That means it's something like this 啦嚇 ，OK 係啦。So 1 kg and 2 kg 啦嚇。Now when you consider the force diagram, or we call the three-point diagram, I didn't talk about this, but because you have learned about this already. But this is the three-point diagram, is the diagram showing all the forces acting on the object. So if talking about the force acting on the 1 kg object, the weight will be 1 times g, is it mg 嘛？ And you know that there should be a normal motion acting on the 1 kg object, because 1 kg object and 2 kg object are touching each other. Okay. And let's take a look at the 2 kg object. Can you tell me how many forces are acting on the 2 kg object? So let me give you the polar. How many forces are acting on a 2 kg object? Now there should be 3 forces acting on the object. So 3 forces acting on 2 kg object. So 1 kg are in contact with the 2 kg. So there's a mutual normal action acting on them. And there's also a it's touching the ground, so there should be also a normal motion acting on 2 kg object. And there's also a weight, is it 2 times g? Can you tell me the magnitude of N and also R? Any human beings can answer? Or any aliens can answer this question. So what is the magnitude of the force N and R? Why? Well, any living organism can answer. No. where n may be just 1 times g 咯。The 1 kg object is at rest 咁啊，we have done this example 㗎啦，do we? If you're talking about r, it should be n plus 2 times g 咯。Is it difficult? That means 3 times g 咯。Now we can find out easy. We can find out very easily if you consider 1 kg and 2 kg as one object, okay? So then this one object has a mass 3 kg. Then R should equal to its weight if the object is at rest. Do you agree? 好啦 done. 好啦 then let's take a look at the third force, okay? The third one is called the tension. So tension is actually the attractive intermolecular force on something string-like object lah, okay? Now it may not be just like a string lah, or any object lah. It can act on a rod lah, a spring lah, whatever lah, just string-like object lah. So why there's a tension then? Now let's consider there's a string. Like, 好，好啦 K is using his his foot, okay, to pull this string apart from each other, okay. Why the string does not break? Because there should be, because his foot is too weak. No, maybe because because K's foot is too smelly, and then the molecules inside the string is very united. Yeah. So what they do there? So if someone is pulling them apart from each other, so there will be a intermolecular. So that means between the molecules there's actually an attractive force that preventing the object from breaking. So this intermolecular force that's the cause of the tension. Okay. So let's take a look at one. Let's take a look at the direction first. Okay. Now for its magnitude, it's quite similar to normal motion. We cannot know about the magnitude unless we apply the Newton's second law, or unless we know all other forces. So then we're talking about the direction. So this is a attractive force. But it's quite confusing if I say that this force is an attractive force. So I will say this is a pull on the object. You know, pull doesn't mean it's opposite to push 㗎嘛，係咪？ And this force is also along the string. So let's take a look at one example here. So this is the object. If you're pushing it with the string, or with 3 fingers, okay. If pushing it with string, on a smooth surface, we don't talk about the friction yet. Then the tension acting on the object. Now this is a tension. We use a symbol T, okay? We use a symbol T. Now this is a tension acting on the object. Now because due to the Newton's third law, so this is also a tension acting on the string. Yeah. So any question on the direction of the tension? So this is a pulling force. no objection 啊嘛。wait a minute, my mouse 好。Now then let's take a look at some other complicated example. So or like this Now you draw the tension by yourself. Now in this case, okay, you are pulling this object by a force, okay, you don't need to consider what force it is. So I want to talk about another example. This is a pulley. Object A and object B. So the two string, there's one string, or there's two string if consider this is also a string. So can you draw all the tensions acting on object A and object B? So I give you maybe 1 minute to do it. Now after a few minutes, the object B on the left hand still very lonely. No one want to touch it. Now that's correct, okay? The string acting on the force, the tension acting on the object A and object B is upwards. This with other direction does not depend on the masses of object A and B. So no matter whether A is heavier than B or B is heavier, it doesn't matter at all. I mean the direction. So for the object on A and on B on the left hand side, so this is a pulling force. So this is a tension acting on the object B. So this is a tension acting on the object A. Okay. Any question? Any question? No. So then let's why you like you type your question or you speak up. Can I explain for which one? Because this is a pulling force. Do you know what is meant by pulling force? First of all, do you agree that there is a tension acting on object A and object B by a string? I think obviously yes. Is it? And then you need to think about the direction of the tension acting on object B. Now, first of all, you should know that this is pulling force. If you don't know what is meant by pulling force, then let's think about another one definition. Okay, so this is the direction of force is acting on the object is pointing from the object to a string. Or you think another way, do you think that the string is pushing the object B in this way? If the string is pushing the object B in this way, that means the object B is moving to the left. But it's weird, is it? And also it's impossible. Then let's move on. Let's take a look at one more complicated example. So how about the tension on the pulley? Can someone take this challenge? Can someone take this? Now, indeed, the tension on the pulley is quite complicated. So on top there's a string, so there's an upward tension acting on the pulley by the upper string, and this is one string connecting across the pulley. So if you're talking about a tension, so this end with there's a tension pulling the pulley downwards, and this end also has a tension pulling this object downwards. So in total, there are three forces. Sorry, if you include the weights acting on the pulley, so in total there are four forces acting on the pulley. I can't explain this very easily, but in you may remember this one. 好啦，嗱 we finished talking about the tension Then let's go on to talk about the first another law that we need to use. So I would say that there's a spring force. It's quite similar to tension, okay? So for spring force, I think we have learned about one formula. There's a Hoax Law. Do we? You did. So the formula is Fe of negative kx. So what is k mean? What does k mean? Anyone? Anyone? Now k is a spring constant. So, or you can call it the force constant. So what is x? Now x is the extension of the spring. So why there's a negative sign? The negative sign means the direction of the force is opposite to the direction of extension. Yeah. So let's say this is a natural length. The natural length means it means the original length without any forces acting on the spring. Okay. Sorry. I should write it with the pen in the Word file. So natural length, it means the length of the spring without any forces. So if you extend the spring a bit, then this is extension. But the extension is to the right. So therefore the force acting on the object should be on the left. Okay. So therefore they are opposite to each other. Now we are going to talk about one complicated concept about the Hoax law. Now let's go back to the textbook. So we're going to talk about this part. Okay, I'm lazy to write it down again. So there's some typo in the textbook. Yeah, there's some typo. So you change the sign here to negative sign. 好啦，now we are talking about the equivalent spring constant. Now the spring constant K depends on the spring, depends on the stiffness. I don't think you know this term, but it depends on how tough or how stiff the spring is. Okay, I can't. It really depends on the number of turns per length of the spring. It depends on the radius of the circle of the turns. It depends on the thickness. It depends on the material. Depends on many things. So whatever, okay. One spring, if you're using the same spring, the spring constant doesn't change. That's it. So in some questions, okay, there will be more than one spring. Then we need to take a look at. We need to apply this skill to combine them together to make the question seem more simple. So let's take a look at if they're connected in parallel. So you know this one is called in parallel because they're in parallel. Now, if they're in parallel, okay, if you move the object a bit, these two spring will have the same extension. These two spring will have the same extension. And what I want to do is we just want to replace these two spring by one spring. Of course, if you replace them with one spring, this spring may not have the same spring constant as these two. And then we are going to find this K equivalent. And also, of course, if you extend this object by 1 cm, we also consider this case you extend it by 1 cm. So that means they have the same extension here, same extension. And because there are two forces acting on, so there's two springs connected to this object. So there should be two forces acting on the object. So the forces acting, these two forces have the magnitude k1x and k2x. Okay, if the extension is x. Then if you consider it's just one spring here, That means you're combining these two forces together. Then the force will be just K1x plus K2x. Okay. That's equal, okay? So that's equal to the force on just by this spring. Then we say that, okay, if we just replace it by one spring, we just say that the KEQ times x. That is the force by this equivalent spring. Okay, then you can just cancel out the x, then you can get this formula. So that's the that's the idea behind. Okay. So in short, that means if the two springs connect in parallel, you can just replace them by one. With the spring constant, that is the sum of the two springs. Any questions? No? Then let's move on. Let's take a look if the two springs are connected in series. I think I need to explain it here because it's a bit more complicated. So if the two springs are connected in series, so K1 and K2. Now if you push the object, let's say if you push the object by 10 cm, what can you tell about the extension of the two springs? Abhijit, what can you tell about the extension of the two springs? That is 10 in total. Now, let the extension of the spring K1 is x1. The extension of the K2 is x2. What we know about it is the sum of the extension of these two springs is 10. Do you agree? I can't explain it explain it it's just by common sense. Okay. So this is the first thing. So the second thing is, you know the object is connected with the spring 2, just with this spring. So therefore the force acting on the object by a spring will be you can just express it as K2x1, right? K2x2. And then now we consider a very weird point. Now let's consider the contact point of these two springs. So this contact point, so on the left hand side there's a spring 1, on the right hand side is a spring 2. So therefore this contact point has there are two forces acting on this contact point. So there are the two spring forces by the two springs. So this one will have the magnitude K1 x1, this one has a magnitude K2 x2. And these two forces must equal. Do you know why? Now you may say that because the object is at rest, the force on the left hand side should equal to the force on the right hand side. Yeah. You may consider like that. But indeed, even the object is moving, these two forces is still equal to each other. Why? Because let's say we apply the Newton's second law. So and then if we apply the Newton's second law, the net force will be K2x2 minus K1x1. Is it? Because they're in opposite direction. And then let's say this object has the mass m. Now that's equal to ma. Then it seems that these two forces are not equal to each other. But we do have one assumption when we're talking about the spring. We consider all the springs are light. So that means they don't have any mass. So then the M will become 0. Okay? M becomes 0. Then that's why K1x1 equal to K2x2. Okay? We need to apply these skills later on when we're talking about the tension along the string. We'll talk about this next lesson. But let's go on to derive it. Now what we want to do, we just want to combine these two springs by 1. The sum of extension of these two springs is x1 plus x2. So therefore, we also say that the extension of this spring will be x1 plus x2. Then the force by acting on this object by this one spring will be just k times x1 plus x2. That should equal to k1x1. Sorry, if that should equal to the force here, that is k2x2. And you know k2x2 also equal to k1x1. So you get this formula. Can you derive? Okay, I'll give you some time to derive it. So I want you to express the k in terms of k1 and k2 only. So I'll give you some time to do it. And also remember, so there are two equations. You may say this one is there. This is one equation, and this is another equation. So I hope you're able to simplify it. It's just some algebra that you can do. Okay. So I'll remind you there are two formulas here. So one is k1x1 equal k2x2. Another one will be this one. So what I would like to do, maybe you just do substitution, no, is it? I don't think it's difficult to do substitution at all. You need to make sure that you know the target. What do we want later on? So we want to eliminate the x1 and x2. So what I can do, let me express the x1 in terms of x2 or x2 in terms of x1. Either way, okay, we'll do. So x1 equal to x2 divided by x1 times x2. Then you substitute in this formula. No? Can you see that you can cancel out the x2 in this formula? Or you take the x2 out in the expression on the left hand side. Then you can cancel out the x2 now, is it? And the final answer for k is k1 times k2 divided by k1 plus k2. Or in other words, it can express it in terms of 1 over k equal to 1 over k1 plus 1 over k2. So that's the formula. Okay. So that's how we combine the two springs connected in series. So I want to stop here first today. So next time we'll go on to talk about the remaining, remaining two forces. So one is the buoyancy, another one is friction. Maybe also air resistance. Friction is the most complicated force. You may take a look at some video about the buoyancy first. But for friction, okay, you may take a look at the textbook, and you may just take a. I don't think any textbook will talk about this quite in deep. you may take a look at some university textbook about the fiction, if you like. I'll send you one. Okay, then see you all on Saturday. Any questions? No? No questions? 好，then see you next lesson.